Alright, so today I'm going to discuss leptons. Leptons are one of the fundamental building blocks of nature, the other one being quarks. Now, quarks exist in groups and form larger particles. Leptons, however, usually at least, exist on their own. Now, like quarks, there are 6 different types, or flavors, of leptons that are split into 3 generations. For the first generation, we have the electron, which I'm sure you've all heard of, and the electron neutrino. For the second generation, we have the muon and the muon neutrino. And for the third generation, we have the tau and its corresponding neutrino. Now, these last 2 generations are a lot heavier than the first generation. This means that generations 2 and 3 are a lot less stable, and thus those particles will very rapidly decay into a first generation particle, just like for quarks. Now, for leptons, there are actually only 3 things that we can measure. We can measure a lepton's mass, we can measure its electric charge, and we can measure its spin. We cannot, however, measure its color charge. That is because leptons are not involved in the strong force. And the strong force is the reason that quarks have a color charge. Now, I'm sure you've all heard of mass. And, because these are subatomic particles, we measure it in mega electron volts per the speed of light squared. Now, the reason this is a measure of mass is because energy, which mega electron volts is a measure of, is equal to mass times the speed of light squared. Now, if you divide both sides by the speed of light squared, you see you can get mass. So thus, this is a measure of mass. Now, because we don't measure a lot of things in mega electron volts per the speed of light squared, I'll provide a translation. So 1 mega electron volt per the speed of light squared is equal to 1.783 times 10 to the negative 30th kilograms. So that way you'll have it in, at least I wish, more familiar units. Now, as for the mass of each of the leptons, the electron has a mass of 0.511 mega electron volts per the speed of light squared. Its neutrino has a mass less than 2.2 times 10 to the negative 6th. For the muons, and by the way, this is the Greek symbol for mu, because muon, it has a mass of 105.658. And the muon neutrino, mu there, has a mass less than 0.17. Now, it is less than because data collection on these particles isn't supremely accurate, so we only know that it's less than this mass. But for the third generation, the tau, we have its mass at 1,776.84 mega electron volts per the speed of light squared, and the tau neutrino is at less than 15.5. But there we have it, the masses of the 6 flavors of leptons. Now we have electric charge, which you've also probably heard of, but are likely not as familiar with it as you are mass. Now, electric charge is a measure of the amount of current traveling through something in a given time period. It is often measured in coulombs. However, because this is quantum physics, we measure it differently. We measure it in an elementary charge. Now, E is relatively often used to represent the elementary charge. However, because we are already using this to represent the electron, that is the symbol for that, we are instead going to abbreviate it with Q, which is also often used to represent charge. Now, one elementary charge is equal to 1.6 times 10 to the negative 19th coulombs. Now, this may seem like a slightly arbitrary number to choose for the elementary charge, but in fact, this was chosen because this is the amount of charge on a proton, and protons and electrons have equal charges. So, you can probably guess what's coming next, but the electron, muon, and tau all have a charge of -1 elementary charge. Shocking, right? Now, all of the neutrinos have no charge, which is why part of the word neutral is in neutrino. You know, neut. Now, the final thing we can measure for leptons is spin. Now, spin is confusing. There is no large-scale example that we can really give. The best analogy I can make is that the particles behave as though they have angular momentum, or are spinning. However, they're not actually spinning, so it gets confusing. Now, because these are matter particles, all leptons have a spin of 1/2. Now, for quarks, it stops here. However, leptons go a bit farther. Say we have two paired electrons. For example, an electron pair in the same orbital period of an atom. So here we have our atom, and here we have our two paired electrons, right there. Now, for two paired leptons, they cannot have the same spin. They have to have opposite spins. So, we'll say one of these electrons has a spin in the up direction. That means the other electron must have a spin in the down direction. Leptons cannot have the same spin. They have opposite spins. So those were the 6 different flavors of leptons. Now, it is possible that there are more than the 6 different types. However, those are just the ones that we've discovered. But there may be more than just the 3 generations. Now, as with quarks, each lepton has its own antiparticle. Now, the antiparticles have the same mass and the same spin as the regular particles. They just have the opposite charge. So this means that the antiparticle for the electron, which is called the positron, has a charge of +1 elementary charge. Now, all of the names for the other antiparticles is just anti and then the particle name. They don't get a fancy name like positron. But, hope you enjoyed it, hope you learned something, and see ya!